Friends, I am Dr. Prof.Chishty and I am teaching physics to the BSc first year students. My today's topic is interference in the thin films due to the refracted light. In our previous lectures, we studied about the interference in the thin film due to the reflected light. So here I will teach you about the refraction in thin films due to refracted light. So let us study here that this is the thin film of thickness T, upper surface, lower surface. On this thin film, there is a ray of light which is allowed to incident. It is supposed as it is refracted in this medium, in the thin films, and then at this point B, this is the point A, this is the point B. At this point, partial refraction take place. This is the emergent ray, and this is the internal reflection, that is the refracted ray. Okay. Now, at this point also, the ray of light will be reflected internally, and it will emerge out. So we can say that there is refraction from the lower surface as well as from the upper surface. If I draw here a perpendicular normal, it is the angle of incidence. If I draw here the normal, then this angle is angle of refraction. Okay. You can join this so that this angle is also angle of refraction. Now I will draw one perpendicular from this point, okay, to another ray, from the point D to the another ray, and this is the point, suppose N, so that after refraction, when these rays are coming out, then this distance becomes equal, means they are traveling the same distance from the point D and from N. So I will draw here also one perpendicular BM. Okay, this angle is 90 degree. So there is a path difference between these two rays, and I want to calculate that path difference. So this path difference x between these two rays is equal to mu BC plus CD minus BN. Now how come? Mu BC plus CD minus, up to this point these rays are traveling equal distance from this point N and point D, but before that this ray has traveled additional distance, that is equal to from B to C and then C to D. This distance is additional distance, and then you have to subtract this much distance BN, as this distance BC and CD, these distances are traveled in medium of refractive index mu of the thin film. Then I will have to multiply it by mu BC plus CD minus BN. So now I will find out the value of Bn using the formula of the Snell's law. Mu is equal to sin I by sin R. This is the Snell's law. Sin I can be written as, in this triangle, sin I here can be written as Bn upon BD. This is the angle I. This is the angle R. So in this triangle, in the triangle D and B, Bn upon BD is the sin I, and in this triangle MD upon BD is the sin R in this triangle. Okay, this angle is 90 degree. So BD get cancelled, and you will get here mu is equal to sin I upon sin R. Sorry, mu is equal to Bn upon MD. Bn upon MD. So Bn can be calculated as mu MD. So I will substitute this value of Bn here, so that x becomes mu into BC plus CD minus mu MD. Now what is BC plus CD? BC plus CD, and this can be equal to this distance PD. So for this I can write here PD, x is equal to mu PD minus mu MD. So I will take here mu common, then x will be equal to mu into PD minus MD. PD minus MD. PD minus MD. And it will become here mu PD minus MD, it will be equal to PM. See here, PD minus MD. So it will be equal to PM. Now my aim is to find the value of PM. So for that purpose I will use this triangle. In the triangle BMP, this triangle, I will write here cos R is equal to PM upon BP. PM upon PB. PM is the adjacent side of this cos R and this is the hypotenuse. So this distance is t, small t thickness, it is also small t thickness, therefore cos R is equal to PM upon t plus t. This distance is t thickness, it is also t, 2t, t plus t. So value of PM is equal to 2t cos R. So I will substitute this value here for the path difference. Therefore path difference is equal to 2t mu, 2 mu, here mu is there, mu t cos R. This is the path difference for the refracted light. Okay. Now if suppose this path difference is equal to n lambda for the bright band, point to be bright, then this path difference should be equal to n lambda. It is the condition for the interference. So I will write here 2 mu t cos R is equal to n lambda. This is the condition for the point to be bright, where mu is the refractive index of the thin film, t is the thickness, n is any integer, n is 1, 0, 1, 2, 3 and so on. Lambda is the wavelength, R is the angle of refraction. Okay. Now for dark point, I will write here path difference should be equal to 2n minus 1 lambda by 2 or 2n plus 1 lambda by 2 depending upon the value of n. Here the n is starting from 1, 2, 3 and so on. If you take 2n plus 1, it will start from 0, 1, 2, 3 and so on. So 2 mu t cos R should be equal to 2n minus 1 lambda by 2. This is the condition for the dark point. Okay, point to be dark. Thank you.